Welcome to this explainer. If you're like most people building with AI right now, you've probably hit a wall where the model just isn't giving you what you want. The prevailing wisdom for a long time has been to just feed it more instructions. But today, we're going to uncover why simply dumping more text into your prompts is actually a massive mistake. Instead, we're going to look at exactly what top developers are doing right now to build truly reliable systems by treating an AI's working memory as a highly curated space.
There's a great quote circulating in the industry right now. Most people try to fix bad AI answers by writing bigger prompts. That's a wrong move. And it's so true. If you've been padding your prompts like you're trying to hit a word count on a high school essay just to get a decent answer, you're falling into a really common trap. The industry is actively shifting away from chasing the elusive perfect prompt, and today we're going to dig into the new discipline that's replacing it.
Here's our roadmap for today. We'll start with the big prompt trap, then define what context engineering actually is, break down the 7-layer context stack, walk through a 4-step agent framework, and finish up with curating for reliable agents. Section 1. The big prompt trap, and why longer context isn't always better.
Modern AI models boast these incredibly massive context windows. Some of them can practically ingest an entire book in a single go. But treating those windows like an infinite bucket is a trap. It actually degrades performance. Think of it like trying to find your car keys in a hoarder's living room instead of on a clean desk. When a window is filled with way too much data, accuracy takes a nosedive. The model just becomes distracted by irrelevant or stale information. Errors quietly sneak in, which is especially dangerous in multi-turn agents, where the chat history and outputs from external tools start to snowball.
So when you hoard context, you are literally inviting 4 primary and often totally silent failure modes right into your system. First, there's poisoning. This is where a hallucinated fact gets into the context, and the AI just reuses it over and over. Then you have distraction, where the model gets so fixated on its massive history that it forgets to make a fresh, logical plan. Third is confusion. This is when extra, totally unrelated details subtly nudge the model toward the wrong answer. And finally, clash. That's when 2 pieces of context secretly contradict each other, and the model ends up picking the wrong one. Knowing these failure modes is step 1 in diagnosing why your AI is going off the rails.
Section 2. What is context engineering? Moving beyond the perfect prompt.
Okay, so the crucial thing here is distinguishing between 2 very different concepts. Prompt engineering isn't dead. It's still super useful for figuring out how you word a request or structure your instructions and constraints. But context engineering is an entirely different beast. It's the dynamic assembly of absolutely everything the model sees at runtime. We're talking about fetching the right tools, the right facts, and the right history, all assembled instantly before every single model call.
Basically, context engineering is the practice of curating the smallest possible set of high-signal tokens to steer the AI's behavior. You really have to start thinking of the model like a human brain with a very limited short-term memory. Your job isn't to dump a massive encyclopedia on its desk and say, figure it out. Your job is to curate only the highest signal, most relevant information it needs for its exact next step.
Section 3. The 7-layer context stack, or what goes into the model's brain.
Every robust context stack is built on 7 specific layers. The first 4 set the foundation for every single call you make. Number 1 is instructions. These are your system prompts and guardrails, where clear, plain language wins every time. 2 is user input, which is just the specific request happening right now. 3 is retrieve facts. And remember, we aren't dumping whole databases here. We're just injecting the few snippets of data that matter in this exact moment. And 4 is tools, which are the descriptions of the functions the model can actually call to get things done, like running a search or reading a file.
The final 3 layers are what keep the model perfectly on track. Layer 5 is short-term notes. This is where the model remembers recent changes, like, hey, we already checked that folder, scan the next one. Layer 6 is long-term memory, which holds stable, on-demand facts about the user or the project itself. And lastly, Layer 7 is the output format. Think JSON schemas or specific examples that strictly lock down the final shape of the AI's answer. When you deliberately curate all 7 of these layers, you get a highly focused, highly capable AI.
Section 4. The 4-step agent framework and building reliable AI with log-look.
Let's actually put this 7-layer stack into practice. We're going to imagine a hypothetical Azure security helper, and we'll call it the log-look agent. To transform log-look from a basic chatbot making random guesses into a really sophisticated collaborator, top developers are using a 4-step loop: write, select, compress, and isolate. Let's break down exactly how this works.
Step 1 is write.
This means giving our agent, LogLook, a scratch pad that exists completely outside of its active context window. Instead of forcing the AI to juggle all its thoughts, intermediate results, and plans in its active memory, we let it write them down externally. So, LogLook might keep a running bulleted list called investigation steps, showing what it's already checked. It keeps the working memory incredibly clean while safely preserving that long-term progress. Step 2 is select. This is where we use precise retrieval to fetch only the specific data needed for this one exact turn. The key mindset here is strict selection, definitely not hoarding. When dealing with messy log files, we found that hybrid retrieval, mixing keyword and semantic search, usually beats just relying on embeddings. So for LogLook, we're not sending over the entire day's server logs. We are explicitly pulling just the top error bursts from the last hour.
Step 3 is compress. You want to keep the valuable signal but drop all the noise. We do this by periodically summarizing long, rambling interaction histories into short, loss-aware recaps. This completely stops the model from dragging a massive, irrelevant chat history into every single new call it makes. For example, the system might keep LogLook's 5 most recent findings completely raw just for safety, but anything older than that gets tightly rolled up into a simple 3-line summary.
And finally, step 4 is isolate. We sandbox different tasks by assigning them to specialized subagents. If you give one single agent a massive, multi-part job, a noisy piece of data can leak over and poison the entire context. So LogLook splits the job up. It uses a reader subagent that just extracts facts from the logs, then a score subagent checks those facts against a security policy, and finally a writer subagent takes those findings and composes the final summary. Each one gets its own pristine context window, which pretty much eliminates confusion.
Section 5. Curating for reliable agents. The takeaway.
By fully embracing context engineering, we are fundamentally changing how we interact with AI. We stop dumping giant chunks of text into a prompt window and just crossing our fingers. Instead, we start treating context as a truly scarce, valuable resource. It is the strict discipline of curating high-signal data. And honestly, it's the only way we move past building simple, erratic chatbots and start engineering complex, robust AI collaborators that you can actually rely on. So the next time you sit down to build an AI agent or map out a new system, I want you to ask yourself one absolutely critical question about your AI's working memory. Are you just hoarding context, or are you actually curating it? Think deeply about that, because your answer is going to make all the difference in how your system performs. Thanks for joining me on this explainer, and I'll see you on the next one.